This conference will now be recorded.
So, good evening. Today we are going to discuss linear momentum, Newton's second law of motion, impulse and impulsive forces, etc. This is under the chapter laws of motion. So, today basically, excuse me. So, today basically we'll be discussing second laws of motion, Newton's second law of motion, and what is impulsive force and what is impulse. Those things we will be discussing. And obviously, linear momentum is one of the important physical parameter in the laws of motion. So, we'll first learn what is linear momentum. Then we'll go to discuss the famous law, Newton's second law of motion. So, you might be thinking, sir, why is it so important to learn what is linear momentum before we go to Newton's second law of motion? It is important because we are going to see in the first law of motion, it was just dealing with net force 0. So, if you remember the statement, if external applied or net external force on any object is 0, then what will be 0 again? The acceleration will be 0. That means object will move. If some object is moving, that will move with a constant velocity. Okay, constant velocity. That means there will be no change in the velocity. If some object is at rest, it will remain at rest forever. So this was actually the first law, Newton's first law of motion. So, but this second law will be dealing with net force not equal to 0. Okay, that means on any object, if there is some net external force, how the motion of the object will change, or how the external force is affecting the motion of any object. So this is external force, which is a net force. This is net force is 0 over here in this second law of motion. So when we apply a force from outside, and what are the physical parameters which is going to be affected due to this external force? See, whenever we discuss or we just see the effect of something, we'll see there will be some changes to some parameters. So in this case, the linear momentum is the parameter which will give us the idea how actually external force affects the motion of any object. In fact, we'll see in the previous case, in the first law, net external force was 0, then acceleration was 0. But in this case, since this is not equal to 0, obviously we can expect that acceleration also will not be 0. So in this case acceleration will be there, and things like that we'll be discussing today to observe and analyze the effect of the force on the motion of any object. We need to define a physical quantity that has a direct relationship with the force, okay, and that is actually linear momentum, or singly sometime it is written as simply momentum. So that's why we need to learn what is linear momentum. So I'll just brief out what I tried to say. I just want to mention that if we apply net external force to any object, how this force is going to affect the motion. If we want to analyze that, we need to have a physical parameter which has a direct relationship or which can change with the external applied field. Okay, so that parameter is the linear momentum. Okay, so that's why we have to learn what is linear momentum, how it depends on various parameters. Okay, so that thing we'll learn first. So linear momentum of an object is a physical quantity possessed by that object due to its motion. Motion means there should be non-zero velocity. Okay, then only you will have linear momentum. Obviously we'll see what is the definition. The definition is this: the linear momentum is defined as the product of mass and the velocity. See, linear momentum is denoted by small p. If you want to write in terms of vector, you can write it. Okay, and it is the product of mass and the velocity. Product of mass and velocity. So this is the velocity. Since velocity is a vector quantity, so any vector quantity if you multiply with any other scalar quantity or constant quantity, that product also will become a vector quantity. That's why linear momentum is a vector quantity. Sometimes it is called simply momentum. Okay, why I'm saying this as linear momentum? Because there is something called angular momentum also, that we'll learn in the 7th chapter. Okay, in the rigid body part or rotational motion there will be angular momentum, that we'll learn later. So we have seen what is momentum. It is actually denoted by small p, sometimes capital P also, and it is mv in terms of vector. Okay, so it is actually see, it is directly, p is directly proportional to m as well as v, velocity and mass. You might be thinking, sir, can you give me some physical example so that I can understand what is momentum? See, I'll just give you a simple example. Suppose you have a small stone and you have a big stone like this. Okay, now it has some mass, small m1, and it has m2, and m1 is much less than m2. Now you do one thing, do a simple experiment. Just keep a glass slab and just take your small stone and then leave it vertically, like just make it to fall vertically down from certain height on this glass. So what will happen? Probably nothing, or maybe there may be little scratch. But if you take the big one, okay, the big stone, and you just leave it from this same height, what will happen? This will crack your glass, isn't it? Crack your glass, isn't it? So what is there in this that it cracks, but the smaller one did not? Okay, there must be some quantity. See, both are stones, both are actually dropped from the same height, and from kinematics we know both of them has actually the same velocity when they come to ground. Freely falling bodies, whatever mass maybe, they will have the same velocity. So what is different here? Since the mass is different, see, the linear momentum is the product of mass and velocity. Even the velocity is same, because of this height is same for both of them, but the bigger mass has greater linear momentum which could break the glass slab. Okay, I'll give another simple example. If you have seen trucks, actually sometime trucks will be fully loaded, okay, and they have to take a turn in a road somewhere. Okay, suppose there is a turn like this. Okay, so there is a road and there is a turn like, okay, I'll just uh, draw it little better. Suppose the lorry or the truck has to take a turn. There are two trucks, suppose one is empty, another one is fully loaded. So what do you think, which one will be requiring much greater force to be applied in the steering to take a turn over here, the empty one or the loaded one? If you had like this experience, like driving car or something like that, or even in that case driving cycle, like a riding cycle also will give you some idea. If you have load in a bag, you have to actually apply. See, you have certain velocity, you have to apply greater force when you have load with you, isn't it? Greater, like you have to apply your brake with greater force, a larger force to stop it. Okay, so this is actually the measure of linear momentum. That is actually measure of linear momentum because of mass and velocity. Okay, mass multiplied with velocity will give you the linear momentum. When you have an object maybe the same mass but greater velocity, there are two masses, suppose two objects with same mass, but suppose this one has velocity v1 and this has velocity v2. Okay, if v1 is greater than v2, then obviously your first object will have greater momentum. That means p1 will be greater than p2. Okay, now slowly we'll see three conditions. I'll just tell you here. See, when I have two objects having the same masses, okay, as I was telling you, suppose there are two objects, okay, having the same masses, they are moving with different velocities. This one same masses, so I'll take both m. This one with v1 and this is with v2. Now let us see what we can write from here, that p1 is equal to mv1 and p2 you can write as mv2. Now if you just take the ratio p1 by p2, then you get v1 by v2. Okay, so what does this mean? This is a proportionality relationship. Proportionality relationship, right? So that means what? Look, if I just draw a curve with velocity, curve of momentum with velocity, it will look like this. Okay, as you increase your velocity, momentum increases. So it will go through the origin, and along this line the mass of the object will be constant. Mass will be constant. Okay, mass will be constant. Okay, now I'll just take the second case when you have two moving objects having the same velocities but different masses. Okay, so I have m1 which is moving with velocity v. Again I have another mass m2 which is moving with the same velocity again. Now you have the momentum p1 by p2 is equal to m1 by m2. So this also tells you the same thing, that p momentum is directly proportional to the mass. So which you can, if you just draw momentum with mass, as you increase your mass momentum will increase, so it will also go through the origin, and along this line the velocity remains constant. Okay, velocity of the object remains constant. Okay, this is second point. Now we'll take another important point here. If you have two objects having the same linear momentum, let us see how it goes. Same linear momentum, suppose I have two masses m1 and m2. Okay, different masses. Okay, so this is moving with v1, this is moving with v2. So I can take the ratio like this: m1 v1 divided by m2 v2. Okay, so as I told, the momentum is same, so same momentum means p1 is equal to p2. Then I can write m1 v1 is equal to m2 v2. So from here I can write m1 by m2 is equal to v2 by v1. So look here, what does this mean? What does this mean? This means that m is inversely proportional to v, or other way v is proportional to inversely proportional to m. That means if you have two objects with same momentum, the velocities are inversely proportional to their masses. Okay, velocity will be inversely proportional to their masses. So the velocities of bodies having equal linear momentum are inversely proportional to their masses. So if you draw this velocity, see, object having same momentum. Okay, if you draw the curve with velocity with mass, then you will get like this, and along this line the linear momentum p remains constant. Okay, so these are few things about linear momentum. Now one important thing is that how this linear momentum is related to the second law, Newton's second law. We'll see that how it is related to second law. Suppose there are two objects, they have different masses. I have m1 mass, m1. I have an object having mass m1. I have another object having mass m2. Okay, so initially they were at rest. Suppose vi is 0 for this as well as this. I'm just supposing that m1 is less than m2. That means this guy is heavier, m2 is heavier, and this is comparatively lighter. Now do one thing, you just apply an external force, same amount of force, external force, same amount of force to both of them. Okay, I'll just do one thing, I'll draw this mass 2 little bigger, maybe like this. Okay, you just apply forces, like two forces to individual objects, but these two forces are equal in magnitude. Okay, equal magnitude or fixed amount of force is given to this object, okay, for same time interval, same time interval. Okay, so what are the points? Points are that the objects are different, having different masses, but they are given same fixed amount of force to both of them, and the time interval of application of the force is also the same. Then what will happen? What will be your natural answer to this question? Like what we should observe? I have two objects m1 and m2, where m2 is heavier. We are giving same force to both of them in the same direction. Initially both of them were at rest. So what will be the natural answer? That the lighter body, from our experience we say the lighter body will actually move faster. Okay, so this move faster. Comparatively, the lighter body will be moving faster. Okay, moving faster. That means the speed will be greater. Okay, all right. For this case also you will see for the same time interval it reaches with certain velocity, obviously. But what you measure, if you can measure the momentum, the change in the momentum, in this case linear momentum, for both of them will be same. The change of linear momentum in this both the masses, even though masses are different, even though these two masses are different, what you look at the end, the change in the momentum for both of them will be the same. Okay, change in the momentum, I say del p will be same for both of them, for both the mass. Look here, I have given a different, like same amount of external force to different objects. They have different velocities. Okay, different velocities maybe. They have different velocities also because this is lighter, this is heavier. But what is same? The same is the change in the momentum, linear momentum, change in the linear momentum. I'll take one simple example, you can understand with that. See here, so what we see, the lighter object acquires greater speed than the heavier one. Then after the end of the time interval, both the objects acquire the same momentum. I'll just tell you one thing. Suppose m1, they have velocity c0 initially, and this is m2. Suppose this m see, I'll just tell you, this may be 5 kg and this may be 10 kg. Just for the sake of example, you take and as soon as you give both of them some 5 Newton force, okay, 5 Newton force, 5 Newton force you just give to both of them, then this may be acquiring certain velocity v1, this may be acquiring some velocity v2, which, like where v1 is greater than v2, but at the end, in this case delta p, and this case also delta p, if you check for the whole process here and for this also, you look the same change, same the change in the momentum, linear momentum, will be the same, even though one is 5 kg, another one is 10 kg, and their force. See, the forces are applied forces on them also same. Then the change in the linear momentum is same for both of them. So actually, this gives the implication, or this gives the important clue to the second law of motion, Newton's second law of motion. So what does this mean? The same force for the same time interval causes the same change in the linear momentum for different objects. And what it implies that it is actually giving a crucial clue for this Newton's second law of motion. You will be understanding very soon. So Deepa, do you understand this philosophy what I just conveyed you? See, I had taken two different objects with different masses. They have been given the same force. Okay, same amount of force they have been given. In fact, they acquire different velocities also, but change in the momentum for both of them will be equal. Okay, so what does this mean? This actually gives the crucial clue for Newton's second law of motion. We'll see linear momentum is a vector quantity. So vector quantity, this linear momentum can change. So vector quantity can change either in magnitude or direction. In some cases there are like changes in the direction, not in the magnitude. Suppose you take you just see this one, vector characteristics of momentum. See, if you just take a stone and tie it with an inextensible string and then try to rotate over your head in a horizontal plane, then what you look actually, see, in this case we have already learned uniform circular motion. What will happen in this? The velocity, linear speed remains constant. Linear speed remains constant, but see, the direction changes always. So that's why the momentum, linear momentum, also changes. So linear momentum means m into v. Linear momentum changes. So if there is a change in the linear momentum, that means what? That is actually, so change in the momentum. That's why you know what you need to keep this stone in a circular path. You need to apply certain force. We had seen in case of lorries or the trucks, I had given you example, like loaded truck has moment greater momentum, linear momentum. To change that linear momentum, you had to apply greater force. Even I can give you another simple example. Suppose you are having a bullet. Okay, bullet, you just throw with something, and another bullet you just fire with gun. Okay, fire with gun. So what you look is that if you have the same bullet but throw with hand and fire with gun, will be different. So which one is actually firing with gun will penetrate many objects, like our like our muscle tissues and all, etc. They can just penetrate through, and it is little difficult to stop the bullet. You need to apply large force to make it stop. Whereas if you have a bullet and if you just throw it, it is easy to stop that bullet. So see, the linear momentum depends on both m and v. So in this case, in case of gun, masses are same. bullet of the gun, masses are same. Only different thing is that for the greater velocity, object has greater linear momentum. And whenever there is a linear momentum, greater linear momentum, you need to apply larger force to change or change the momentum. Momentum means what? Initially, if some object was in motion with velocity v1, okay, and finally you want to make it stop, that means your final momentum will be 0. So it is seen that when you try to stop any moving object, you are applying certain force, and that force is actually the directly proportional to the linear momentum, change in the linear momentum. If you have to change, see some lorry with linear momentum, huge linear momentum wants to comes to rest, it has to be given a very large force to make it stop. So from here you can get the crucial inclination, like clue, that there is there is this law, Newton's second law, that if you apply, like you have to apply greater force to stop an object with greater linear momentum. That means linear momentum is actually directly proportional to the force, external force, applied force. So what is the clue from here? That the external applied force is directly proportional to the change in the linear momentum. So from here we can get a nice law given by Newton, greatest scientist, greatest physicist, as well as mathematician. So what is the second law saying? Let us see the statement. Then you can understand whether this clue is all right or not. So force, external force is directly proportional to the change in the linear momentum of any object. Okay, let us see. So the time rate of change, or rate of change, here I should write time rate of change. The time rate of change of linear momentum of a body is directly proportional to the applied force, and the change in the momentum takes place in the direction in which the applied force acts. Okay, so I hope you understand this. So the time, this is the statement of this law, Newton's second law of motion. The time rate of change of linear momentum of a body is directly proportional to the applied force, and the change in the momentum takes place in the direction in which the applied force acts. Okay, so this is the statement of the law. Now we'll try to understand, or I'll try to explain you what it is. Suppose there is an object of mass m, object, so I'll just write in short. So there is an object, suppose A has certain mass, is applied an external force, okay, F external, or simply I'll write F, capital F. A force capital F is applied to an object A which has mass m, okay, which has mass m, and due to the application of force, the object changes its velocity, or yeah, velocity from v to v plus delta v. Okay, so what it is, I have a I have an object m, okay, small m, small m. This is an object. When it is acted upon by a force, external force F, then the object changes its velocity from v to v plus delta v. So what is the change in the momentum? Change in the momentum means m final, mass final, v final minus m initial, initial mass and initial sorry, this is final mass and final velocity. Anyway, mass remains constant in any kind of motion, so you just leave that with m, and this is final, so this will be initial. Obviously these are initial parameters. So vf minus vi, this is the change in the momentum. All right, now according to the definition, or according to this law, this linear momentum, change in the linear momentum, actually this is change in the linear momentum, is directly proportional to f external, okay, external force. Okay, so this is what it is. So the statement is saying that the time rate of change of linear momentum is directly proportional to the external force. Okay, so this is if, okay, just a second, one. So if this change is happening in 1 second, or in more general, what I can write is, suppose there is a mass m, okay, initial velocity is vi, okay, and it is acted upon by a force f, then mass remains same, it acquires a velocity, final velocity, suppose v plus delta v. Okay, all right. So and this happens during time delta t, okay, delta t interval. Okay, so change in the momentum will be m delta v, right? Now what is the time rate of change? Rate of change, this is the change in the momentum, this is change in the momentum, change in the momentum. But what is time rate of change or rate of change? This is the rate of change of momentum, rate of change of momentum. So this is directly proportional to the F external, the external applied force. Okay, so if you put this this is delta p, so in place of delta p, what we will write, m delta v by delta t is force. What is this del v by del t? So this del v by del t is nothing but average acceleration. So this is the actual, see, average acceleration into mass will give you the force, amount of the force. Now you have, see, you have the force, external force is equal to del p by del t. If you take the limit delta t tending to 0, then you get what is called dp by dt, the total derivative from the calculus definition, from the definition of calculus. So derivative here we'll get like this, dp by dt. Okay, so the time rate of change of linear momentum is equal to the external force, applied external force. All right, now yeah, so this is the statement. Here we'll look that this can be, actually this is proportionality constant, so proportional dp dt. So p is again m v, so m dv dt. So what is this m? This m is mass, which remains constant. What is this dv dt? I hope you remember this is acceleration. So this is the acceleration. So what does this mean? That the force is actually creating acceleration or changing the velocity of any object, or in other words, if there is a rate of change or change of linear momentum, there must be a force applied from any external agency. Okay, so in this case I had given one example that when you have a stone tied with a string and you just rotate it over your head in a circular path, the linear velocity remains the constant, v remains constant, but what changes is the direction, and because of that the linear momentum also will be changing. And if the linear momentum changes, then there must be a force applied to cause that change in the linear momentum. That means to rotate that you need to apply a force. Okay, you need to apply a force. So that force is actually given by your finger, and that is through the string, and this force eventually has another special name that is called centripetal force. Okay, and that will be given by your hand only. So whenever there is a rate of change, so that rate of change will be always directly proportional to the external force applied. Okay, so in this case, see, if we want to get the magnitude of the force or unit of the force, we'll be writing like this. Just remove the proportionality constant, we write k dp dt. Okay, and eventually this k is chosen as a 1, this is a proportionality constant, and this k is chosen as 1. And finally Newton's second law will be used in this form, m dp dt or m dv dt. Okay, so this dv dt is acceleration, so F is equal to ma, which is the famous Newton's second law of motion. F is equal to ma. That means if you apply external force to any object, it will change its velocity, so there will be an acceleration arising in that object. Okay, all right, so we have learned what is Newton's second law, and we tried to demonstrate it. We tried to write the mathematical formulation. F is equal to m dp dt. Oh, sorry, this here will be only dp dt, there will be no m here. I'm sorry, there will be no m here. Here this will be m. So m dv dt, this dv dt will give you the acceleration, linear acceleration in this case. So this is actually the mathematical form, and obviously, see, this can be written dp dt as well. So both the form you should remember. Sometime maybe this expressions will be, or this relations will be required. to solve numerical problems. So force, so we'll just define. Okay, so I forgot to mention the units of momentum, linear momentum. Linear momentum is P, denoted by P. So P is actually given by mv, that means kg meter per second. Okay, kg meter per second. This is the unit for momentum, linear momentum. So this is the SI unit. So SI unit of force, if I want to find out what is SI unit of force, so SI unit of force is actually Newton, that is given by Newton. And CGS, in CGS it will be, so Newton is denoted by capital N. You might be knowing from your previous classes as well. And CGS unit will be actually dyne, and then there will be a relationship between Newton and dyne. Okay, so those things you might have already learned, what is the unit of force. And one more thing you need to remember, that force will generally, in general, linear. Change in the linear momentum will be in the direction of force itself. Okay, change in the linear momentum, direction of change in the linear momentum will be in the direction of force, applied force. All right, so now what we'll learn here few implications of this law. What are the implications? That we have learned that F is equal to m into A. Now if suppose F is equal to 0, anyway mass is not going to be 0, so what is next? This is 0. So what does this mean? Again, if this is 0, then dv dt is 0, acceleration is dv dt, so v is equal to constant. That means what? This is actually, see, from the second law of motion, we can just go back to first law of motion. Okay, that means your second law, Newton's second law of motion is consistent with the Newton's first law of motion. Then second implication is that this law actually strictly applicable for point object, applicable for point objects. Point objects, but this is applied even for extended object also. Okay, it is actually meant for point object, but still we use in approximation, by doing various approximation we use this as applicable for extended object also. So Newton's second law mainly will be applicable for the case of point charges, sorry, point particles. Now the fourth implication is that it is very local. It has actually localized phenomena, so it is actually, so Newton's second law of motion is a local relation. So is local relation. Okay, this is a local relation. So these were few implications. Now what we'll do, we'll learn two more things. Those are, one is impulse and another one is impulsive force. So obviously impulsive force is the cause and impulse is the effect. We'll see what are those. So look, a large force. So what is impulsive force? When a large force acting for a very short time to produce a finite change in the momentum is called impulsive force. Try to understand this. A large force acting on an object for a very short time to produce a large change in the momentum. Sorry, finite change in the momentum. See, large force acting for a very short time period. Can you give me some examples, sir? Yes. Example is, see, if you have seen cricket match, see, the cricketer, they just take a shot, and what is the contact duration between the ball and the bat? It is a very short duration, fraction of second. Okay, so that short period, a huge force is being applied to the cricket ball. That's why there is a change in the momentum. That means, see, if you have to take a a shot of runs, okay, 6 runs. If you want to hit a six, then what you have to do? Actually, cricketers, they have to hit it very nicely and with a very very large force. But the what is the duration of the contact between the bat and ball? Very very short, fraction of second. So that kind of force is called impulsive force. I'll give you similar examples, like say when footballer take a shot, long shot, when they're kicking. So there is a duration when they're taking a shot, duration between the leg, duration between like duration of contact between the leg and ball, football will be very very less. Okay, so there can be very many such examples. Like see, if you are just if you are just hammering a nail. So what is the contact time between the hammer and this nail? It is very very less. Okay, contact time will be very very less. Okay, contact duration will be less. But what is happening? The nail is gradually going forward. So this is the change in momentum. In case of football, contact duration is very very less, but force was large. So there is a change in the momentum. That's why it goes with no time it goes to the boundary. Okay, for cricket ball. Okay, so there is a change in the momentum over there. So a large force acting for a very short time to produce a finite change in the momentum is called an impulsive force. Now see, such a large force actually changes very abruptly. That means since contact period is very very less, so the applied force, it changes abruptly, and you cannot measure the time and the force, like the duration of the contact and the force, you cannot measure simultaneously or separately. You cannot measure them separately. Time and velocity separately, separate two quantities you cannot measure together at the same time. So it is very difficult to measure the force as well as the time period, okay, or the contact duration. So for such cases, the change in the momentum, see, this force is actually is a cause for change in the linear momentum. So if you know the change in the linear momentum, then you can estimate from there what is the amount of force or the duration of the time. So impulsive force, sorry, impulse. So that is called actually impulse. So when you apply a large force for a short while, it will have some effect on the object. That is the change in the linear momentum. So this change in the linear momentum is actually called impulse. You are applying impulsive force, which is a cause, and it is making an impulse, which is effect. So impulsive force is cause and impulse is effect. Okay? An impulse is defined as the product of the force and the time for which it acts. Suppose there is okay, there is a cricketer who is hitting the ball with the bat for certain time interval delta t, okay, and change in the momentum, suppose delta m, sorry, delta p, change in the momentum delta p. So if the force applied over here is F, then F into delta t will give you delta p. Okay? So the force into time interval will give you the change in the linear momentum. Okay? Or see, I'll just take a few example over here. If you have constant force doesn't change, then you have to get F into t. This will be giving you the change in the linear momentum. Okay, let us see here. See, if I have a constant force, suppose there is some force here, maybe some 10 Newton force. This is the force. It is always constant with time. See, time, so suppose t1 time it starts moving, and t2 time, sorry, t1 time starts applying the force, and there is a duration between them, delta t is t2 minus t1 time interval. Okay, so this is the time interval, and suppose this point is A, this is O, this is B and C. So if the force is always a constant force, then during this interval, what is the change in the momentum? That you can get from this force time curve. This is called force time curve. If you find out the area of this force time curve, then that will give you the change in the momentum. Okay? In some cases, see, you are given the area, see, you are given the parameters like what is the force up to here and what is the time interval you will be given. Okay? But you will be asked to find out what is the force then in that case. Okay, you just take the change in, see, you will get change in the momentum from this area of OA BC triangle. Okay, this is the change in the linear momentum. So we know that F into delta t is equal to delta p. So if you know the time interval, then it is very easy to get the force. What is the impulsive force, amount of the impulsive force? Or if the force is given, time interval is given, then it is easy to get what is the impulse. Impulse means the change in the linear momentum. So if you just get the area of this rectangle, you will get the impulse. Impulse means F into T or dF into dt. So that is actually impulse, product of the force and the time interval. Now if you have a non-linear force or a non-constant force, the force is actually changing with time like this. So suppose T1 here, T2 here. If the force is changing like this, okay, so force is not a constant quantity. So in this case, what you have to do, if you want to get the change in linear momentum, then you have to find out. See, as I said in previous cases, it was simple area. So it is 10 Newton, and this is T2 minus T1. That is the time interval. In this case, you will get the area easily in case of constant force. But if the force is not constant, in that case, you have to do the integration to find out the area under this curve. You have to do the integration. So by doing integration, you can find out what is the impulse. So if I write f, see, f dt, okay, so f into dt will give you integration. See, integration f into dt will be actually giving you the impulse, okay. So we'll take a few examples in the, like, numerical examples in the next class maybe. So what is impulse, like how there are problems in changing the linear momentum in this particular portion, like depending on the second law of motion, how we can solve those numerical problems. We'll take a few numerical examples in the next class in the beginning, maybe 10 minutes or 15 minutes, then we'll take up the new topics. So what we have learned today, what is linear momentum, how is it related to second law of motion. Time rate of change of linear momentum is actually proportional to the external force. So that was the statement, and the change in the linear momentum has to be happening along the direction of the force itself. Okay, and we have learned what is impulsive force, what is impulse, and we have learned the statement, and we had understood, like we have discussed the mathematical form of this second law of motion. This is F is equal to ma. So these are all we have learned today. So Deepa, if you have any question now it is for you. Now if you have some question, you can ask me now. If you have any question regarding impulsive force, or what is linear momentum, how is it affecting the, like how the force is affecting the motion, okay, so you can ask me anything if you have any difficulty in understanding here. So if you don't have any question, then I have to stop it here. Is it okay?